In this lecture, I'll be discussing about a research topic that is designing a magnesium alloy with high strength and high formability. So our research problem is to design such a magnesium alloy which will not only keep the excellent formability but at the same time it will also give us the high yield strength. The combination of both high yield strength and high formability is usually desired. A magnesium alloy with such a great formability but the yield strength is very less, then such type of magnesium alloy will not be desired from our end. So we desire such a magnesium alloy that will be showing both high strength and high formability. Such type of magnesium alloy we have to design. So we will be discussing about different aspects of designing magnesium alloy with high strength and high formability. Let's move forward. So in this discussion, first of all, we will be discussing about the introduction part in which we will be discussing about the magnesium alloy and its uses and the research problems we will be discussing. And then we will be coming to the alloy design concept. What was the concept behind the alloying element selections that we will be discussing. And then also the manufacturing process that we are selecting for the for the alloy that we will be discussing because variety of different manufacturing process routes are available and we have to decide which manufacturing route is good for our alloy design concept. So that we'll be discussing. And then again, then in the third uh, slide, we'll be discussing about the microstructures, what microstructures we have achieved, and according to that, the properties will vary. So we'll be discussing about that. And also the grain boundary segregations, when we will be discussing about the alloy design concept, then a new concept will come, grain boundary segregation. Different alloying element will be segregating along the grain boundary and that will be having a very profound impact on the mechanical properties of the alloy. So we'll be discussing about the grain boundary segregation in the fourth slide, and then we'll be discussing about the textures. As we have discussed about the magnesium alloy have a is needed to improve its formability. Why? Because uh, there is problem with the formability of magnesium alloy. That's why we need to improve its formability. The problem is at the texture level. Whenever magnesium alloy is prepared by thermomechanical processes, then what happens? A strong basal texture is formed in the magnesium alloy, and due to which we are not able to achieve good formability. So we will be discussing about how the texture has changed in the new alloy design concept that we are utilizing. So we will be discussing about that. And the next and the last we will be discussing about the room temperature formability and tensile properties. Let's move forward. So in this slide, we'll be discussing about what is the reason behind the poor formability of the magnesium alloy. Basically, there are two reasons. The first reason is development of a strong basal texture during rolling or thermomechanical process. So whenever there are two processing routes of magnesium alloy, one is the casting method, and other is the rote method. Means we will be using some other methods apart from the casting method, because when we do casting, it becomes much more complicated process, and it is not possible to make each and every complicated and intricate steps using casting. So sometimes we have to use road magnesium alloys also. So when we use road magnesium alloy, we do some type of thermomechanical processing, and in the thermomechanical processing, it develops a strong basal textures, due to which we are not able to achieve the good formability of the magnesium alloy. That is the problem with the formability of the magnesium alloy. And the second reason, because magnesium alloy has an HCP hexagonal closed packing crystal structure, due to which it has very less number of sleeve systems available with it. So we are not able to achieve good formability because it has less number of sleeve systems as compared to other crystal structure system like FCC, BCC. In those cases, we have large number of sleeve systems. But in case of HCP, the number of sleeve system has drastically decreased. So this was the problem with the magnesium alloy formability. Now we have to improve the formability. In what way? We'll try to improve the formability. So there are two ways of improving the formability of magnesium. The first method is by the modification in the thermomechanical processing of the magnesium alloy, the rolling method that we are utilizing to increase formability. So we need to modify those thermomechanical processes. And the second method is by the addition of the rare earth elements. What does a rare earth element should do inside the magnesium alloy? So whenever we add rare earth elements inside the magnesium alloy, that it randomizes or weakens the strong washer textures, due to which it improves the formability. But the problem with the addition of the rare earth element is that whenever a rare earth element is added into magnesium alloy, and by the addition of it, the formability of the magnesium alloy increases, but at the same time, it decreases the yield strength of the material. So we can say that we have an inverse relationship between formability and yield strength of the magnesium alloy. So whenever we try to use the rare earth element, we get inverse effect on the yield strength of the material. So our motive is to increase the formability, but not at the cost of the yield strength. Our yield strength will be maintained up to such a high level that it could be utilized for our purpose. So our concept here in this slide, we will be discussing about the alloy design concept and the selection of application process. So first, we will be discussing about the alloy design concept. So what is the alloy design concept that we are utilizing here? That is different from the earlier researchers. Earlier researcher was utilizing two methods by the modification of the thermomechanical process and by the addition of the array earth element. So by both of those processing methods, we were able to achieve good formability, but not the high yield strength. Whenever we got high formability, the inverse effect on the yield strength was seen. So our motive is to increase the formability of the magnesium alloy, but not at the cost of yield strength. Yield strength should be maintained up to a high level. So for that purpose, we had to use some new alloy design concept, the alloy design concept that was used previously, that was decreasing the yield strength. So we used different alloy design concept. What was the our different alloy design concept is that, so in this case, we tried to segregate zinc and calcium along the grain boundary. So whenever zinc and calcium was segregated along the grain boundaries, it decreased the grain boundary energy. So when it decreased the grain boundary energy, So whenever the recrystallization of the magnesium happens, the grain growth is inhibited. It will not allow the grain to increase in its size. What happens during thermomechanical processes, whenever we do rolling of the magnesium alloy, the grains get elongated, and up to a certain time then it will break. But here, by the co-segregation of zinc and calcium along the grain boundary, the grain boundary energy decreases, and decrement in the grain boundary energy will not allow the grain to increase further. It will maintain its own shape and size. So even if you do for thermomechanical processing of the magnesium alloy with calcium and zinc segregation along the grain boundaries, it will not allow the grain to increase in its size. So it will maintain the grain size, and it will maintain the formability of the magnesium alloy. At the same time, what we do, uh, AL8, Mn5, Al2Ca, such type of intermetallic compound is formed inside the grains of the magnesium alloy that will increase the strength, the yield strength of the material. So we are utilizing two things at a time. The first thing that we are doing, that we are trying to segregate zinc and calcium along the grain boundary, and that is going to increase our formability by decreasing the grain boundary energy. At the same time, the underlying element which we have added in magnesium alloy, it will form an intermetallic compound. And those intermetallic compounds are Al8Mn5 and Al2Ca. So this type of intermetallic compound that is formed inside the grains, that will obstruct the dislocation motion, and that will increase the yield strength of the magnesium alloy. So this is our philosophy that we are using in this alloy. So previously we were using magnesium, zinc, calcium alloys, magnesium, zinc, and calcium alloy. That was giving very good formability because of the zinc and calcium segregation along the grain boundary, but it was not providing very good yield strength. So some other researchers tried aluminum alloying aluminum with the magnesium, zinc, calcium alloy. So when aluminum was added in the magnesium, zinc, calcium alloys, it increased the strength up to a further level, but it decreased the formability. So why it happened? So when aluminum was added in the magnesium, zinc, calcium alloys, what happened? Aluminum interacted with the calcium and it formed an intermetallic compound, that is Al2Ca. So by the formation of the intermetallic compound Al2Ca, we had an intermetallic compound inside the grains that increased the yield strength of the magnesium alloy, but at the same time, all the calcium was utilized to form an intermetallic compound. So the amount of calcium should be that should have been available for the zinc and calcium segregation along the grain boundary, that was diluted. So decrement in the amount of calcium for the zinc and calcium segregation along the grain boundary. So the zinc and calcium segregation decreased. So yield strength increased, but at the same time formability decreased. So in this research paper, authors have utilized an ingenious method, and that method was utilizing manganese. See, utilize magnesium, zinc, and calcium was previously used. Then another author used aluminum to add in this. So when aluminum was added, yield strength increased, but formability decreased. So the author's motive in this research paper was to increase the formability, but not at the cost of yield strength. Our yield strength should be maintained. So the author utilize the beneficial effect of the zinc and calcium segregation along the grain band, and also the effect of the intermetallic compound. Intermetallic compound formation inside the grain will improve the yield strength of the material, whereas the zinc and calcium segregation along the grain boundaries will improve the formability. And by the formation, when aluminum was added, and by the formation of Al2Ca compound, calcium was not available for the zinc and calcium segregation along the grain boundary. So our purpose was to increase the availability of calcium along the grain boundaries along with the zinc, but at the same time we should have formed some intermetallic compound inside the grain also. So the author did some thermodynamic calculations with manganese, and she found that when manganese will be added inside the magnesium, zinc, calcium, aluminum alloys, then what will happen? It will form an intermetallic compound with aluminum, and that is Al8Mn5. So when Al8Mn5 is formed, the possibility of forming Al2Ca is decreased, because the gives free energy is more negative in case of aluminum and manganese. So the tendency to form Al8Mn5 is more. At the same time, the tendency to form Al2Ca is less. So all the magnesium will be utilized to form an intermetallic compound Al8Mn5. So now no aluminum is available to react with the calcium. So when no aluminum is reacting with the calcium, now all of the calcium is available to get segregated along the grain boundaries. So almost all of the calcium is getting segregated along the grain boundaries now, and at the same time, an intermetallic compound Al8Mn5 is forming inside the grain. Very less minute amount of Al2Ca is also formed inside the grain. So we are getting the effect of both the things. Means we are improving formability, and at the same time we are maintaining yield strength of the magnesium alloy also. How we are improving the formability by the co-segregation of zinc and calcium along the grain boundaries, and at the same time we are forming an intermetallic compound like Al8Mn5, Al2Ca. Such type of intermetallic compound is improving our yield strength. So this This mechanism or this new alloy design concept was utilized to form a new alloy with high strength and high formability. So this was the concept behind it, and now we had to select a manufacturing method. Which manufacturing method we will utilize? That was the problem. So initially, we used the conventional cast ingot method, and in that method, alloy was allowed to solidify with the passage of time. So much time was allowed for the alloy to solidify. So that increased the grain size. So in this case, we tried twin roll casting. In case of twin roll casting, what we are doing, there is rapid solidification. Rolling is being done along with the solidifications. The molten magnesium alloy is directly put into the roller, and that roller is moving, and along with the movement of the roller, magnesium alloy is getting solidified, and at the same time rolling is being done. So the solidification is very fast. So in this way, we get very fine grains that will improve the formability. So this is the microstructure that we have developed.